So, good afternoon to one and all present here. So, this is going to be a semester-long unofficial course on electrodynamics. Most of you are already having your official courses on electrodynamics. You have your reference books, you have a lot of other things. So, what I'll be trying to do throughout this course is this, that I'll try to show you what real electrodynamics is. Because the challenge of the fact is that electrodynamics heavily relies on vector calculus. Generally, people, they do not go through vector calculus very thoroughly, so for that reason they do not understand electrodynamics very well. And even then there are sophistication and complexities of electrodynamics that I think should be appreciated. Most of you are somewhat familiar with electrodynamics from your high schools, you have had seen elementary treatment of it. If some of you would have read a bit more sophisticated books, you may even be well aware of what the Maxwell's equations are. We'll be coming to that in a moment. But as any course starts, as the course is electrodynamics, we would like to talk about the motivation to study electrodynamics. So first and foremost, we do understand that there are fundamentally four kinds of forces. So till date, any force that we have observed, we can keep it into one of four categories. The four categories are, the first being gravitation, the second being electromagnetism, which we will be concerned with this semester. The third being the strong nuclear force, or something that is generally referred to as the strong force. And the fourth being the weak nuclear force. So the gravitational force is the kind of force which is exerted between two particles by virtue of their mass. That is, if I take two particles which have, or two bodies which have mass that are in a sense massive, they are going to exert a force on one another. In electromagnetism, we take a look at forces which occur due to the virtue of charge. Something which a lot of people do not understand is that there's a reason why we call it electromagnetism. Basically, electricity and magnetism for a very long time were seen as two different phenomena. But then, using something which we call the Maxwell's equations, they were unified in a sense. More importantly, what I would like to go over in this course, which I don't know whether you will go over in your official course or not, is something that in some sense, since you guys are aware of electromagnetism from your high school, I would use a bit of terminology, but we'll come to that later as well. So we have got electric fields and magnetic fields. We describe the entirety of electromagnetism using both of these fields. But the matter of fact is that we call it electromagnetism because these fields are not two separate fields, in the sense that they are the manifestation of the very same phenomena. So something that you are familiar with is something called the special theory of relativity, right? You guys went over that last semester, and something which you would have seen is that a lot of phenomena is frame dependent. That is, you have heard of or you have studied phenomena such as length contraction, also called Lorentz contraction, and time dilation. That is, the length of a certain object may appear different to two different observers. That the time interval between two events may be perceived as different to two different observers. Similarly, in some sense, electromagnetism is also bound with relativity. That is, what appears as electric field in one frame may appear as a combination of electric field and magnetic field in another frame. The reason I would specifically like to go over this course is that more or less you guys know what electricity is, you guys know what magnetism is, you have studied it in depth. We'll just introduce a few more mathematical tools in order to help or facilitate our calculations. So there's not a lot of new things that you are going to learn, but I believe this is definitely going to be new. One of the reasons why we came up with special relativity is that it was Maxwell's equations that predicted that the speed of light is a constant. which is one of the postulates, as you know, from the special theory of relativity. So Maxwell's equations predict that in a given medium, the speed of light should be constant for all observers, or there's a paradox related to it, which can be resolved through this postulate. That is, something arises, which we'll come over, something arises in Maxwell's equation that does not agree with the Newtonian mechanics. So one way to deal with it is to introduce the postulate that given any medium, the speed of light is constant for all observers. So we'll be coming over that, and that is how special relativity, in short, if I was to tell you what exactly is it that we are going to conclude, that it is relativity that gives rise to magnetism. In order to give you some feel of it, assuming that you guys already have some knowledge of the subject, comes from Faraday's law. What does Faraday's law state? It states that if I have a coil and the flux through it is changing with time, it gives rise to an electromotive force. And then yet again we include the Lenz's law there and we come up with a conclusion. But if you look at it, one of the easiest ways to produce EMF is to take a coil, take a bar magnet and move it to and fro. So it is using a relative motion that you are creating electric field using magnetic field. So in some sense, relative motion and relativity, things like these are very deeply connected with electromagnetism, and in this course, I would spend a fair amount of time going over that as well. Then we come to the strong nuclear force and weak nuclear force. As the name suggests, it is the speciality of these forces are that these are only observed at the nuclear scale. For example, yet again, assuming a bit of knowledge, most of you are familiar with the Coulomb's force. So if I take two positive particles or two masses which have positive charge, they would repel one another, right? But all of us, since we were in high school, have accepted the fact that an atom has a nuclei which has a lot of protons all tied together in a very small volume. How is that possible? And then we claim that electromagnetism is a way stronger force than gravitation. It is stronger by something of the order of it is stronger than the gravitational force by something of the order of 40. That is, which we'll also see, that if I consider two electrons, the electrostatic force between the electrons and the electrostatic force between the electrons is about 10 raised to the 40th power stronger than the gravitational force between the electrons. That is an exercise that we'll do soon enough. Then there's the weak nuclear force. It is observed in radiation experiments such as there's decay experiments, and most of you would have studied about it, though if needed you'll have a course in nuclear physics as well if you guys choose to take physics major in the future. So that is it. Now, so in order to appreciate what electromagnetism is, I would like you all to wonder about the fact that it is the force that we are most familiar with. The point is, since to us a lot of things are normal and are preached to us since our childhood, it becomes very normal to us. We become very indifferent to the wonders of the world. So if I was to give you one such example, this is a duster. It has some mass m, right? And because it has some mass m, the earth exerts a gravitational force on it. If I assume the gravitational field to be a constant, which is a good approximation, the earth, the entirety of the earth, all of us, one another, everything that has mass in the universe is pulling it. Effectively, since we are on earth, the earth is pulling it downwards. But I, a mere human, who has no mass compared to the entirety of the earth, as if my mass was to be removed from the earth, it would make no difference or no significant difference to the mass of the earth. And yet again, I can hold it against the force of the entire earth pulling it downwards. That may help you appreciate how strong the electrostatic force actually is. That the electrostatic attraction between my hand and this duster is stronger than the gravitational force with which the entire earth is pulling this duster. And when I let it go, So in order to yet again appreciate it numerically as well, since most of you are familiar with Coulomb's law, we'll do a small calculation. So what does Coulomb's law state? If any of you may help me with it. Have any of you ever seen experimental verification of the Coulomb's law? As in, have you ever seen Coulomb's law in action? So to give you incentive to attend the next class, if you guys decide to attend the next class, I'll make you see with your very own eyes that Coulomb's law indeed works. We'll try to do an experiment which is going to demonstrate that Coulomb's law is indeed true. So what does Coulomb's law state? Anybody of you?
The force between 2 point charges is the product and the distance. Square of distance.
So if I take 2 point charges which are separated with distance r, the force between them, the magnitude of the electrostatic force between them is given as K q1 q2 upon r squared. Q1 q2 is the magnitude of the charge on these bodies, and r happens to be the distance between them. K happens to be the Coulomb's constant, which in SI unit is approximately equal to 9 into 10 to the power 10 raised to the 9th power Newton meter squared upon Coulomb squared. So the thing is, what we are going to do now, and yet again even the gravitational force is somewhat similar. You have G into M1 into M2 upon R squared. So we are going to do something about this. So what we are claiming is that if I consider two bodies, one body has mass M1 and charge Q1, another body has charge Q2 and mass M2. And the distance between them is r. They are separated by a distance r. So what we wish to calculate is the ratio of both of these forces. So if I was to calculate the ratio of both of these forces, that is F electrostatic upon F gravitational. Mind you, I am just considering the magnitude of both of these forces. So it is going to come out to be this particular value. Now what I want to calculate is, what I want the particle 1 and particle 2 to be is electrons. So I want to calculate this, exactly this ratio for 2 electrons, and let us see what ratio do we get. So we insert the value of K, that is 9 into 10 raised to the 9th power, and then Q1 and Q2, since both of them are electrons, they have the same charge, so it becomes E squared, and where E is given as 1.6 into 10 to the power minus 19 squared upon G, if I'm not wrong, is given as 6.67 into 10 raised to the minus 11 into mass of both of them is yet again going to be same, because the mass of the electron in the rest frame at least is a constant. So it is going to be 9.1 into 10 to the power minus 31 squared. Now since I have a bad memory, please make sure that these are in the right units and the right powers. So could any of you please calculate this for me? Okay, so let us see. So we have 10 raised to the 9th power, and this is 10 raised to the 19th power, negative 19th power into 2, which is going to be 10 raised to the minus 38th power. So we have a minus 38 here. In the denominator we have 10 raised to the negative 11th power. If it comes to the numerator, this is going to be plus 11, and this is going to be minus 31 squared, which is minus 31 into 2, which is going to be minus 62, and when it comes to the numerator, it is going to be plus 62. So I have taken care of the powers of 10. Now I need to take care of the rest, which is 9 into 1.6 squared is 2.56. and I have 6.67 into 9.1 squared is approx 81. Fine, then we'll go with 81. And then I can cancel the 9 here, I get a 9. Let us approximate this to, let us try to get a smaller value, let us approximate this to be 7. So what is 256 upon 63? Somewhere around 4, I can take this to be 4 because 64 upon 256 would have been 4. So this value comes out to be approximately, and can you calculate this for me? 2 plus 1 is going to be 3, 3 plus 9 is going to be 12, 1 carried, 6 plus 1 7, 7 plus 1 8, right? So it is anyways going to be 73 plus 9 82 minus 38. So 82 minus 30 is 52 and minus 8 is, sorry, what did I calculate again? I was so down. 73, 80, 2 minus 38. So 52, 52 minus 8 is 44. So as you can see, like I said, it is somewhere around 40 magnitudes stronger. Maybe I don't know why I have a feeling that I took one of the constants to be wrong, or maybe we made a few approximations. You can cross check it, but at least what we can see is that the electrostatic force is way stronger than the gravitational force. And you can see all of that. It's like the chalk on the board. The reason why it sticks to the board, though the entire mass of the earth is pulling it downward, is because the electrostatic attraction between the chalk powder or the chalk particles in the board is greater than the entire force with which the earth is pulling down the chalk particles. So that is why it is very important to study electromagnetism. Every time you shake hands with someone, every time you hug a person, every time you touch something, any interaction of any sort, it is related to electromagnetism. Electromagnetism has made our lives very easy. You have got lights in this room, you have got air conditioner. At your hostels you have got heaters. Heaters, as most of you are well aware of, it exactly uses the Joule heating effect. That is, it uses the Joule heating. That is, excuse me, when electric current flows through a resistance, it produces heat due to the resistance in the wire. And we'll come to that as well. Since I'm working with somebody who happens to be an expert on superconductors, maybe we'll also talk a bit about superconductors and semiconductors. But that is the plan. So even when we consider about light, though it has a lot of descriptions, one of the particular descriptions of light happens to be that of the electromagnetic wave. Though you guys are not aware of the wave equation yet, which you will learn in the next semester, I'll try to teach you enough wave equations so that you can at least appreciate what the electromagnetic waves are about. That is, light in some sense is an electromagnetic wave. In fact, there's a very interesting story related to it. So what happens is this. Maxwell tries to measure the speed of light. Fine? So Maxwell tries to measure the speed of light, and he comes up with a number which is very close to the constant that we know today, c. Now what happens is, I'm really sorry, the speed of light was already known. Maxwell was trying to study the speed at which electromagnetic waves propagate. So c was already known to a very nice approximation, though we still have got better and better measurements nowadays. But to a great precision c was known. What Maxwell does is, Maxwell tries to measure the propagation speed of an electromagnetic wave. And what he realizes is that the speed always comes very close to c. That is, it is in experimental error precision, you could say, that the number, the speed at which the electromagnetic wave propagates, happens to be very close to c. That is how one of the major ideas that we have today, even in modern physics, was proposed. All of you would have studied about dual nature of radiation and matter. So one of the major ideas that light, though it may not be quantum mechanically right to say so, but in layman terms shows a dual nature. Light shows particle characteristics as well as wave characteristics. So the wave characteristic story, it was Maxwell who came up with it. In fact, Maxwell's equations are very special in the sense that the electromagnetic equations, they change based on which unit system are you using. That is, if you are writing the Maxwell's equations in the CGS unit, where the unit of length is taken to be the centimeter, the unit of mass is taken to be gram, and the unit of time is taken to be second, in a lot of equations, c or either c squared appears as a constant, hinting at its very important nature, which, given special relativity, we already know, which we will revisit again in this course. Any questions this far? And you may even ask me questions that have not been discussed yet, that is completely fine, because I may not go over all sorts of topics. So, any questions? Anything that you went across in the class and you were not able to grasp, or anything of that sort? No questions? Okay, then we'll move on. So we are done in some sense with the introduction of electromagnetism. Now coming to the Maxwell's equations. Though what Maxwell's equations are is the culmination of the majority of electromagnetism. For example, when we talk about classical mechanics, the major equation that we come across is F equals to mn F1 equals to minus F2. These two equations in some sense describe most of the, what could you say, electromagnetism. If I was, most of the classical mechanics. And if I was to think about gravitation, it was Newton's law of gravitation, somewhat referred to as the universal law of gravitation, that at least is a good approximation to the gravitation that we understand. Similarly, what Maxwell did was, using four equations, though those equations were not of his own, he was, you could say, half of the equation, that is 3.5 of the equations are attributed to other scientists, but 0.5 of the equation is attributed to Maxwell. But like I said, Maxwell's genius came, which we'll see, I'll not talk about it right now, but Maxwell's equations happen to be important in the sense that using just four of the equations, you can describe the entirety of the electromagnetism phenomena that you see around you. More importantly, why this course is important is, it is going to teach you a lot of things about physics, in the sense that you guys take this law for granted, but this law happens to be incorrect. It is not necessary that if one particle exerts a force on another particle or another body, the other body will exert an equal and opposite force on the first body. At least, this is incorrect. To some extent, you could say this is true. When electrons move at very high speeds, we observe forces that are equal in magnitude, but they are not directed opposite to one another. For example, if I have two particles, it is not necessary that the forces or the opposite pair of forces, the action-reaction pair, would always be directed along the line joining them. This is why
The electrostatic forces is
electrostatic force happens to be a central force. Like I said, electrons.
they're moving. You're considering that they're moving, right?
No, what I'm considering is, except for electrostatic forces, there are other forces as well. For example, electrostatic itself comes from two words, electro and static. Static means at rest. When we deal with electrostatics, we assume that at least most of the charges that we are talking about, for example, you would have seen general problems where you have n number of charges and you are calculating the force due to these charges at another charge. You can let this charge to be free, but all of these collection of charges, usually we assume them to be at rest. Okay? But what I'm trying to point out is, there are forces other than electrostatic forces as well, which two charged particles may exert on one another. One of the examples is that when electrons travel at very high speeds, near speeds comparable to the speed of light, another force becomes dominant, which does not obey Newton's third law.
Electrostatic force obeys that law.
Yeah. The electrostatic force does obey that law. The electrostatic force is a central force. So if you guys remember, the central force has the definition that the magnitude of the force is a function of the distance between both the particles, and the force is directed along the line joining both of these particles. So, yeah. So, the way usually courses are done are these. You go through the 4 laws and then you write it as Maxwell's equations. But since I have to motivate you to take up vector calculus, in fact, one of the inspirations for vector calculus was Maxwell's equations. For example, you do know that calculus as a subject was developed in order to study motion, though we consider Leibniz to be a co-founder of calculus, but calculus is mainly attributed to Isaac Newton. Why did Isaac Newton invent calculus? Why did he come up with calculus? Because he wanted to study motion. So therefore, the physics motivated the mathematics. So the physics motivated the mathematician to come up with a new framework of mathematics. Similarly, most of vector calculus was discovered or was worked upon in order to ease up the Maxwell's equations, that is, to ease up their representation. If you have a chance, go look at Maxwell's original works where he gave his 4 equations, and you would see very long, gigantic equations, right? If I'm not wrong, it's called a treatise on electricity and magnetism. But anyways, if you search Maxwell's original work on electricity and magnetism, you'll be able to find it. So I'm going to now write the 4 equations of Maxwell, in case I remember that. Or at least I'll be writing this first. This is how the 4 equations of Maxwell are written down. Now, if you notice, these are written down in notations which I think most of you are not new to, but I would still tell you. This is called the del operator. It is something which comes out of vector calculus. If you take a dot product with this del operator, which is in some sense a vector, you get something that we call a divergence. That is, if you take the dot product of del vector with another vector, you get something called the divergence. If you take its cross product with another vector, you get something which we call the curl of the field or the curl of the vector. And if you consider its, if you operate the del vector on a scalar such as temperature, what you get is something that we call the gradient. So if you look at it, there is not even a single law of Maxwell which we write without del operator, which comes from the vector calculus. So it is indeed very important to study these laws, to study vector calculus in order to understand these equations. But then what I would also like to point out is that none of these equations are new to you. This is something that we call the differential forms, all of these, since these are written in sense of the del vector, del operator, which has something to do with partial derivatives. If you remember, if you don't, we'll go over that as well. So del operator has something to do with differentiation. So we call this form of the Maxwell's laws the differential form of, not Maxwell's laws, sorry, Maxwell's equations, the differential form of Maxwell's equations, right? If I write these in their integral form, you will be able to understand each equation very well. You'll be able to recognize them, in fact. So the first law says you guys do recognize this law. This is Gauss's law, that is, the net electric flux through any closed surface is proportional to the charge enclosed by the closed surface. Coming to the second law, it is nothing but yet again Gauss's law for magnetism, which says that the net magnetic flux through any closed surface is zero. We'll come to this as well, but in some sense you understand flux to be electric field lines or magnetic field lines. These are concepts that you do understand. Even if you do not understand, we'll eventually come to them. So what this says is that if I take any surface, no matter what, the number of magnetic field lines that leave the surface is equal to the number of field lines that come inside the surface. This gives rise to yet another very beautiful property, that is something which you would have just, sorry? Exactly. Magnetic monopoles do not exist. That is, if I take a bar magnet and I break it into two parts, it's not like I have now a north pole and a south pole. For example, I can have a positive charge and a negative charge, two opposite poles of electricity, but I can never have two opposite poles of magnetism, in the sense that if I take a bar magnet and I break it into two, rather than having a north pole and a south pole, what I have now are two new bar magnets with north and south pole. It would break in this manner. This is the north pole, this is the south pole. Let us say I break it in between. Now this would become a south pole and this would act as a north pole. And we would come to in detail on Gauss's law of magnetism as well when the time requires. Now this happens to be, if I'm not wrong, correct me if I am, I believe it has something to do with and here you write it as EMF. You guys recognize this, right? This is Faraday's law of electromagnetic inductance, and using Lenz's law, you give it a minus sign. If you remember, it opposes the change in flux due to which it was created, and we'll come over that as well. This, if you remember, is nothing but the Ampere circuital law. That you consider an Amperian loop, the line integral of the magnetic field on that loop would be equal to mu naught times I enclosed. But none of these were given by Maxwell. First two by Gauss, third by Faraday and Lenz, fourth by Ampere. But Faraday made a small correction. That correction factor was this. He argued about something, that is, if I change the magnetic field, it would give rise to an electric field. And if you guys remember a bit, we were told that the induced electric field is a bit different than the electrostatic field. It is not conservative in nature. And we'll also come to what does it mean for a force or a field to be conservative in nature and what not. But I'm also trying to cater to people who already remember a bit of electricity and magnetism from their class 12th. So these are the laws that we are going to study. Of course, you need to add a Maxwell correction factor there. But so this is the integral form of the Maxwell's equation. But like I said, in order to appreciate its beauty, we need the differential form as well. And in order to get the differential form, in order to be able to comprehend the differential form, we need something called the vector calculus. We'll have to ask ourselves, what does a surface integral mean? We'll have to ask ourselves, what does divergence mean? What properties does it show? Can I calculate divergence for every function? If I calculate divergence for if I cannot calculate divergence for every function, can I use some other method to get through all of that? But the point I'm trying to make here is that a vector calculus is extremely important to understand. Does everybody get that? Any questions this far? Okay. Now the reason why I did not like Griffith is this. Griffith throws at you a bunch of mathematics as soon as you open the book. The first chapter is called, if I'm not wrong, it's called vector analysis, right? It's called vector analysis. It throws a bunch of mathematics at you. It It asks you the question what a vector is, what a tensor is, how is a vector different from a tensor, or what is a tensor's rank, what's a gradient, what's a curl, and what not. But it does not motivate the fact that why do we need to study vector calculus in order to understand electrodynamics. I showed that to you right now. And now what I'm going to do is, since all of you are right now going through Gauss's law in your class, which says in its integral form, I would like to talk about the surface integral, right? So what we are going to do is we are going to discuss what does it mean to have a surface integral, so that when I teach you surface integral, in the back of your head, you do know that why exactly do we need the surface integral. We need the surface integral in order to evaluate the left-hand side of the integral form of Gauss's law. And since its differential form states that the divergence of the electric field is equal to rho upon epsilon naught. Epsilon naught is the constant which you call the permittivity of free space, which, if I am not wrong, has this value. And you can calculate its unit using the fact that the Coulomb is constant. So basically, all the units would be such that it would be opposite or the inverse of the unit of the Coulomb's constant, which, if I am not wrong, should be Coulomb square upon Newton meter square. Alright? What does rho represent here? Rho represents the charge density. And though in some sense we do understand what charge density is, but like most things, we would try to get a mathematical idea of what exactly it means to call something a density, so that we can understand how to manipulate it. There are two things. There's one thing to understand something, and there's one thing to understand something good enough to be able to manipulate it.
Charge density, if there is a point charge, then
That is exactly why I said we have to come up with this, and we'll see how the charge density works. But for that matter, okay, I'll give you the answer to your question. What do you understand by charge density?
charge per unit.
Charge?
Linear charge density.
Okay. So generally speaking, since I'm using rho, we use that for volumetric charge density. And because anyway in Gauss's law you're considering a closed surface, so you're considering a volume in some sense, right? So what we are trying to say here is that, loosely speaking, this is not the exact definition, but we'll come to it as well. The charge density happens to be this. So the charge density is charge per unit volume in some sense. Then we must ask the question, what charge and what volume? Well, you're free to choose any volume. If I want to ask you, what is the mass density? It does not make any sense for me to ask what is the mass density. I must specify over which volume. If I was to talk about the mass density of this duster, you would consider the volume of this duster, consider its mass, divide them and give me the average mass density. If I was to talk about the mass density of the duster and the table beneath me, you would calculate the volume of this table, the volume of the duster, consider its entire mass, divide it and give me the average mass density. So in a similar sense, when you ask me what is the charge density of a point charge, you'll have to also specify which volume are we talking over. For example, this is a point charge. What is the average charge density over this volume? 0, because in this volume I have no charge. What is the average charge density for this specific volume? It would be the point magnitude of the point charge divided by whatever volume this shape occupies. So this is how you define.
But like this is a point charge, so the surface of the circle is the Gaussian surface, right? So we're dividing the charge by the volume of the Gaussian surface. We take a charge sphere.
Consider a charge sphere already. Do you want a hollow charge sphere or a full one?
No, solid.
It's hollow.
Solid.
Solid, okay.
Solid charge sphere. We take the standard mass.
Sorry?
Charge in its mass level.
Okay, the entirety of the mass. So the charge is uniformly or non-uniformly for that matter distributed in the entirety of the charge sphere.
And then we consider a Gaussian surface also.
Gaussian surface, what surface do you want me to consider?
At R, a Gaussian surface which
Okay.
we calculate here.
This is in some sense a 3D diagram. So we have a sphere and a smaller hypothetical sphere which happens to be a Gaussian surface. Alright.
Now, how will we calculate this?
Okay, that is exactly what we will come up with. But before that, okay, fine. Before I go to the surface integral, I'll go to the charge density. But before that, since all of you have taken a course on mechanics, or rather two courses on mechanics, I would like you to answer the question: what do you mean by speed? Sorry? Distance covered upon time t. Is that instantaneous speed or average speed?
Average.
Okay. So the claim being made is average speed, since I'm lazy, is d over t. Okay. Agreed? Then we agree that d is the total distance covered in time t and t is the time t. Time interval t rather. What is the instantaneous speed?
When we take the limit of
T
when we take the limits at a particular
Then I ask the question, what is the average charge density?
Volume will be take 0 and tends to
Change in volume.
oh sorry, average, sorry.
Whatever value I have considered, whatever volume I have considered, I consider that, and then I consider the charge in that volume. So then I ask you yourself, what is the linear charge density at some xyz point in space? I'm not about linear, since this is a volume thing, I'm asking you. Similar to what you said is, if I was to write it more properly, this is the average speed. And when I asked you how do I get to the instantaneous speed, you said take the limit delta t tending to 0. So this is the average charge density. Now I'm asking you, how do I get to the charge density, the volumetric charge density?
take the limit of the volume, that volume approaches to
So I keep on shrinking the volume, and what I get is agreed?
This is instantaneous kind of something.
Yeah, this is instant, and I'll tell you how. This is a very interesting idea, and I went over it in the mechanics course as well, so I did not go over it properly. I'll go over it now again. This is a very interesting idea. Yeah, we don't need this anymore. We are done with this. We'll use this now. So I asked the question. Imagine a particle moving along the x-axis. It is constrained to move along the x-axis. This function gives me the position of the particle, the x-coordinate of the particle, as a function of time. So I ask the question, what is the velocity of the particle or the speed of the particle at t equals 2 seconds? Do it, guys. The class seems very lazy for some reason. People are tending to fall asleep and
15.
stuff. Sorry?
15.
15. So I see x at 2. All this means is x evaluated at t equals 2 to be 15, and I assume the units were meter and second. So this is what I'm getting, rather the speed at 2 or velocity, whichever one you want to take. Now the question is, what does it mean for the speed to be 15 meters per second at t equals 2 seconds? This is an important question and one of the crux questions of calculus, because you are telling me that at t equals to 2 seconds, if I look at the car, I'll see that it is moving with 15 meters per second. So I would like to draw an image of the car. I ask you to calculate the speed for the position. The speed is 15, right? And what is the position at 2? Calculate it, guys. 10.
11. No, 10, sorry.
So this is my origin. This is x equals 10 meters. My car is here and it's moving with 15 meters per second, right? But then this is all I have. This is an image. How could something still, because to talk about t equals to 2 seconds means that exactly at t equals 2 seconds, I clicked an image of the car. So it does not make any sense to say that at t equals to 2 seconds, the car was moving at 15 meters per second, because it wasn't moving at all. Because in order for motion to happen, you need time interval, right?
We take 1 to between 1 and 2 seconds.
That we'll come to that as well. So what I'm trying to ask is that it does not make any sense to say that the car is traveling at 15 meters per second, because particularly for any motion to happen, we need a time interval, not a time. But then to say at t equals to 2 seconds, it does not mean anything, because t equals to 2 seconds is a time moment, it's a time instant, a time coordinate, it's not a time interval. So the hidden assumption here is this. I would, for my simplicity, rather take an easier function of time. So I plot x as a function of t. It comes out to be a parabola. Fine? Sorry. So the point now I'm trying to make is, I need a time interval in order to calculate the speed. So I want to calculate the speed at t equals to 2 seconds. So I go at t equals to 2 seconds and I get the position coordinate there to be equal to 4. Now I wish to calculate the speed. For that I need a time instance. So I consider another time moment, which is 2 plus delta t, where delta t tells me the increment in the time, or if delta t is negative, the decrement in the time. Now for this specific time interval, I can calculate the average speed. So how do I do that? I simply write the average speed is the same as delta x over delta t, which means the value of x at some 2 plus t minus the value of x at 2 upon the time interval yet again is, like I've said, it is delta t. This gives me the average speed. Now, there's something called a limit. If the limit of the function exists, what we are going to observe is, as I decrease delta t from either of these sides, for example, if I have to consider a positive delta t, let us say if I consider 3 seconds, so I get the average speed between 2 and 3 seconds. Then, if I consider the delta t to be 0.5, I'm going to get the average speed between 2 and 2.5. If I have to consider it even smaller, between 2 and 2.1, between 2 and 2.01, between 2 and 2.001, the smaller I keep on making my delta t, I would see that if a limit exists, and I think it would be way too far-fetched to walk into the limits concept in this course. If you want, I can give you a reference from where you can read it. If the limit exists, what we would see is that as the delta t becomes smaller or larger from both the sides, we see that there's a particular value to which I can get as close to as I want. For example, if I claim that the velocity at t equals 2 seconds happens to be 15 meters per second, so you can ask me that give me this delta t, the value of delta t, such that the average speeds happens to be 14.999999 as many nines as you want. I can give you a delta t no matter how much close you want my speed to be to 15 meters per second. I may not be able to give you a delta t where my speed is equal to 15 meters per second, but no matter how close you want to 15 meters per second, I can give you that value. I can give you a delta t such that when you calculate the average speed, you would be that close to 15 meters per second. So that is what we mean when we say that there exists a time at t equals to 2 seconds. It's just that the delta t is very small. As in, the smaller delta t gets, the more my average speed tends to 15 meters per second. We define linear charge density in the very same sense because I'm talking about a particular volume, right? So even if no matter how much I shrink my volume, I can never get to a point because the linear charge density at a point has no meaning. Just like the speed has no meaning at t equals to 2 seconds. So did I say linear charge density? Forgive me, I meant volumetric charge density. So just like the speed has no meaning at a particular time instance, the volumetric charge density has no particular meaning at a point in space. If I claim that this is equal to a particular value for some x naught, y naught, z naught, let us say 1, 2, 3, 1, 4, 3, whatever you want to take, if I claim that this is equals to rho naught, what I'm claiming is that no matter how close you want the value of the volume charge density upon this point to be to rho naught, I can give you a delta V naught small enough that you can get as close to rho naught as much as you want. So that is what I mean. Just like the instantaneous speed at a time instance has no meaning unless and until we think in terms of limits, the volumetric charge density at a particular point has no meaning unless and until we think in terms of the limit. Did everybody get what the volumetric charge density is? So now, in order to answer your question, I would like to ask you another question. Let us say I have d in the x direction to be this denotes the velocity or dx by dt to be equals to 2. Whatever 2 units you want to take, you're free to do that. I ask you at what position was I, and did I give you dx dt equals to 2? Let me know. At t is equals to 1 second, where was I? Or rather, in some sense, if I was to consider my displacement along the x direction, if I was to, rather than asking you x, if I was to ask you delta x, how would you tell me that? In some sense. So, if I give you dx dt is equals to 2t, how would you give me delta x from here? As in, like, it would come out to be a function of time, but let us say, how would you give me delta x from here? So we'll integrate it, right? So dx in that case would become 2t dt. We integrate both sides. Dx would come out to be delta x, and we would get this to be 2t square plus 2 plus c if we do not have put the appropriate limits. And this in that case would be x if we put the constant to be c. The 2's cancel out. You get x to be equal to 2 square plus 2 plus x is equals to t square plus c, right? Similarly now, we ask the question, if you are given the charge density at a particular point, I'm not going to write x, y, z every time. It is understood that I'm talking about the volumetric charge density at a particular point. If I am to give you the linear charge density, how do you figure out, like you asked, the charge enclosed by a particular volume? Yet again, we will do the same thing. dq will be equal to rho dv. We integrate both sides. If we put in the limits, as in we want to integrate, as you said, if I was to consider the volume that you talked about, it starts from r equals 0. If I was to think somewhat in sense of polar coordinates, it starts, because then we'll also have to discuss what do we mean by a volume integral. So we start with the surface integral and then we'll move to the volume integral. But in some sense, what you are doing here is you are taking the integral over the entire volume. So you take the volumetric charge density and you consider its integral over the entire volume, and that is how you get your charge.
You were doing volume integral.
Yes. Sorry?
Limit is 3D then.
Yeah, that is 3D. That is what we'll come to. So when you deal with volume integral, the way to write volume integral would be, you would write your dv as dx, dy, dz.
In high school, you were doing just a closed integral. So what is the difference?
So what the difference is that the surface integral can be taken over any surface. It need not be closed. Something that you would have learned in high school is that Gauss law is only applicable in case of symmetry, where it is easy to evaluate the volume integral, right? You use it in order to find the electric field for symmetric systems such as a charged sphere. You use it to form the find the electric field due to a linear charge density, that to an infinite one, and some other cases as well. So the thing is, in that case it becomes very easy for you to calculate the surface integral. But you did not do dx, dy, dz because you already knew that the surface integral, the volume integral, if I take my rho to be constant, I can take it out. And all the volume integral means is that take small volumes and add it all up. So you know it would be a sphere. In order to further illustrate it, I'll solve the case of the point charge using Gauss's law. So let us consider a point charge Q. I want to find the electric field due to point charge Q at a distance r from it. So since, at least for now, we do believe that Gauss law only works in case of symmetrical systems, and I have to form a closed surface. So I want a symmetrical system about this point charge. So a good guess would be to consider a sphere of radius r around this point charge. So now you have it. In this case, what you can simply do is, well, if I was to consider q equals rho dv, you don't even need to integrate here. You can directly use the q that you have been given. Or in some sense, let me see. What you would rather have here is, depending upon your radius, you can figure out, what would you say? You can figure out the average charge density here. However, in this case, you would not require it. You can still solve it using the Gauss integral. You would argue that the elements you are talking about, though, would also come, what does the area element mean? What does the normal vector mean? What you would argue is that due to symmetry, the electric field will always be pointing outside from the sphere, and any area vector, since area vector is now perpendicular to the plane, any area vector would be parallel to E. Since EdA simply happens to be EdA integral, and since the entire case is symmetric, you can argue that the electric field would be constant for a particular r. You take E out and you integrate this dA. Like you said, we just integrated the dA or the dV. So the point here is, you simply know what the surface area of the sphere is. So you write 4 pi r square. But as Professor Sheet would have said if he was taking an electricity and magnetism course, we are not in high school anymore. How come you know that the surface area of the sphere is 4 pi r squared? That is the question that we need an answer to. So it is by the virtue that you have memorized something that you can put it right here. But had you not memorized it, in order to get this 4 pi r square, you would have to consider all these small areas over the sphere and integrate them. So that is why here you would just directly do a dV or dA, because you remember that the volume of the sphere happens to be 4 by 3 times pi r cubed. But how do you know that? You have just memorized it. It is through such surface area integrals that you will actually be able to tell, that indeed the volume of the sphere happens to be 4 by 3 pi r cubed. Here you have taken area, but for in order if you were to consider charge, like you said, since you do know that in order to integrate, we integrate for continuous systems such as this, right? So when I talk about, when you're talking about the charge sphere that you talked about, now it's a continuous volume, charge volume description, something that we have a volumetric charge density. So there what you're going to do is, in order to get the charge, now I get it, I did not want to take the example, I wanted to take the example of the sphere. Is this?
Like in this case, can you apply the volume integral?
No, because you have a discrete charge.
You have a discrete charge.
So integral only happens when you have something of a continuous charge density. Here you have a discrete charge. So it does.
So for finding out the charge, we do the volume integral.
Yes.
And here we have a discrete charge.
Yeah. So you do the volume integral when there's a continuous charge distribution where you want to find the charge. That is when you do the integral. So before we leave, I would like to at least start, because most of this you already knew. There was nothing new about it except I believe just the differential form of Maxwell's equation. So before we leave, I would like to leave you with the idea that we are going to be dealing with. There's something called the functions of several variables. And unlike what I did last time, going completely mathematical, I would rather like to teach you just good enough so that you can do physics with it and still not be mathematically weak. So if I was to remind you, what does function of a single variable mean? You have two sets, A and B. A has some elements, A, B, C, D, E, F, G, H, I, J. Works? All a function does is, it creates mappings. That is, it takes every element of the set from which you are mapping, as in, the direction of the function depends. F A to B and F B to A are very different. It may be that a function can be defined from A to B, but a function cannot be defined from B to A. There can be all sorts of possibilities. So the direction of function is important. So if you are defining the function from A to B, A is your domain, B is your codomain. So the condition for the function to be defined is this, that each and every element of A must be linked to some element of B, but to particularly one element, that is, if you notice here, it is permissible for two elements to be mapped to the same element of the codomain. There is no issue with that. But what is not permissible is for the same element of the domain to be mapped to two elements of the codomain. This is what we mean by the function of a single variable. Because if I was to talk about real numbers, if I take my set to be vector calculus, there's this book called there's this book called Div, Grad, Curl and all that, an informal text in vector calculus.
नाम ही छोटा नहीं है?
ये काफी अच्छी बुक है if you want to study vector calculus. ये आपको सिर्फ vector calculus definitions नहीं देता, at the same time feel देता है. And what I am doing कि Maxwell के law use, I mean equations use करके ही you are going towards that direction, as in you are using Maxwell's equations to motivate the use of vector calculus. वो इस बुक से आता है. ग्रिफिथ्स वगैरह में ये नहीं है. पर्सेल में ऐसा होता है कि जहां जरूरत होती है वहीं इंट्रोड्यूस कर देता है. सो इट इज इम्पोर्टेंट कि आप एक बार में पूरा वेक्टर कैलकुलस सीखें. ऐसे टुकड़ों में पर्सेल की तरह भी काम नहीं चलता, बट ग्रिफिथ्स की तरह भी काम नहीं चलता कि आपको कुछ पता ही नहीं है वो आगे जाके यूज कहाँ होना है. सो इन दैट सेंस दिस बुक इज अ वेरी ग्रेट बुक, एंड ज्यादा बड़ी बुक है नहीं. इट इज अराउंड 150 pages long, but बहुत फैला फैला के लिखा हुआ है, जैसे लोग आंसर शीट बड़ा करने के लिए लिखते हैं. सो यू कैन, अगर मैं इसे 3 लेक्चर में हफ्ते भर में खत्म करूंगा वेक्टर कैलकुलस को, यू कैन वेरी इजीली गो थ्रू ऑल दिस बुक इन अ वीक. अगर 150 पन्ने हैं तो 7 दिन से डिवाइड कर लो, अराउंड 1 दिन के 20 पन्ने. एंड आई कैन टेल यू कॉफी लेके बैठोगे हद मार के 1 घंटे में हो जाएगा 20 पन्ना. हाँ, इफ यू आर अ बिट गुड एट इट, इफ यू आर नॉट, थोड़ा सा टाइम एक्स्ट्रा लग सकता है, बट ये बुक पढ़ना कोई बड़ी बात नहीं है. इसमें तो आधा से ज्यादा जगह तो डायग्राम्स ने ही छेक रखा है, क्योंकि इन ऑर्डर टू एक्सप्लेन देयर आर अ लॉट ऑफ डायग्राम्स, देयर आर अ लॉट ऑफ डिस्क्रिप्टिव इमेजेस. तो 20 पन्ने में 5 पन्ने तो सिर्फ फोटो ही होंगे, 5 से 6 पन्ने. तो यू कैन डू दिस वेरी इजीली एंड इट इज गोइंग टू गिव यू अ गुड ग्रास्प ऑन वेक्टर कैलकुलस, हाउ डज थिंग्स वर्क्स. बट एनीवेज ये खत्म करके छोड़ता हूं तुम लोग को फंक्शंस ऑफ सर्टेन वेरिएबल्स. ओके देन स्टार्ट.
सबका स्टार्ट ही है.
So the thing here is, now I'm talking about a function from the set of all real numbers, which is the set of all real numbers. In some sense, I'm talking about a function of this sort. कि आप एक real number लेते हो, x का जो set है, that is, you know, the domain of x, it happens to be the set of all real numbers. तो तुम हर real number लेते हो, उसका square करते हो और उससे उसे map कर देते हो, right? This is what we mean when we say a function of real numbers or a function of real variables, or at least single real variable. Several variables में कुछ नहीं है. यहाँ पे जो y की वैल्यू है वो बस x पे डिपेंड कर रही है. तो मुझे x की वैल्यू दो, मैं तुम्हें y की वैल्यू बता सकता हूँ. It's almost like an output machine. At least physics में introductory level में ऐसे ही पढ़ाते हैं कि फंक्शन एक मशीन है, इधर से आलू डालो उधर से सोना निकलेगा. But the point I'm trying to make is कि now I can introduce two variables. For example, if here I had y equals to x squared, here I can write z equals to x squared plus y squared. So just giving me one number is now not sufficient. If you tell me x equals 1, I'll ask you what does y equals. Unless and until you give me a pair of variables, I cannot tell you the value of the function. So this function, if you look at it, I'm getting a real number out of the function. So every xy is linked to a real number. So the codomain is still R, right? But my domain, it has now become R2. And R2 is just a fancy way of saying a set where you have taken all possible pairs of real numbers. So 1 के साथ 2 लिंक्ड है, 1 के साथ pi लिंक्ड है, 1 के साथ e लिंक्ड है. हर real number हर दूसरे real number के साथ लिंक्ड है. That set is R2. Alright? So this, when you define a function of two variables, you define it like this. But then you can go even further. You can take R3, that you have x, y, z, and another variable. But then the way to visualize a function of two variables is that all you need is the x and y axis. If I was to talk about the first quadrant of, let us say, y equals x squared, give me any x and I'll be able to tell you y. Because every x here is associated to a y here, right? But if I'm to talk about that particular function, now I need a 3D space. So this is my x, this is my y, this is my z. If I tell you that x equals 1, now there's an entire value of y that it can take, because like I said, in R2, every real number is linked to every other real number. So when you say x equals 1, I can take any of these y values, any other real number, right? And similar, so what is happening is, here I had a line, the x-axis, and above it was every associated y value. But here I have 3D space. This is my xy plane, right? And every point here represents the ordered pair, that is two real numbers. So if I say, give me the value for 1, 2. So what you are going to say is, move 1 units in the x direction, move 2 units in the y direction. This is my point 1, 2. And now above it, like let us say if the value is 5. So along the z-axis, move 5 units. So what you are now getting is, here you are just getting a curve in the xy plane. But here you are getting a surface. That is why I introduced this. So why do we need a surface? We need a surface to perform the surface integral. And why do we need to perform the surface integral? In order to evaluate electric field using Gauss's law. Fine? So the way to go about this is this, that in order to talk about surfaces in the Cartesian coordinate system, what we need now is a function of several variables, that it takes two or more than two variables, real numbers as input, and it produces a real number. So you have
Three variables, then volume.
no, you can talk about volume here as well, because every surface, it's just that when the surface becomes closed, now you have a volume. For example, I'll give you the equation. So how do you draw a circle? What you claim is,
बैटरी कम है एक बार मेन बता दो
we are almost done with that. So this is just the end point. So how do you draw a circle? What you claim is that I have a point and I need the collection of all the points which are equidistant from it. So let's take this point to be the origin. So what you claim is that I take any point xy and I calculate the distance. So what I'm getting is x under root x squared plus y squared is the distance of any point xy from the origin. I take this to be some constant r, which is the radius. I square both sides and I get this, the equation of the circle. However, this is not a function because with every x you have two associated y's. So you would have to specify which branch you want to take, right? Similarly, here if you want to talk about closed surface, all you have to do is, what you are saying is that from the origin, the collection of all points in the 3D space which are at a constant distance r. So what you are now going to get is a sphere. You have your closed volume. But here yet again the same restriction. In the xy plane, if I talk about a sphere, if centered here is a sphere, so for every point there's a point located upward and a point located downward. How similar to in the case of a circle, if this
Sphere exists in XY plane.
sorry,
XY plane, the sphere can't exist, right? It needs three values. Right?
exactly, so you have three variables here. It's just that
It is the XYZ plane, the whole Cartesian, right?
so what's happening here is, look, you have in some sense two variables here in the xy plane. But why do we call it the function of one variable? Because one is the dependent variable and one is the independent. That is, x determines y. So you have two variables xy in the xy plane. But why do we call it the function of x? Because if I give you the value of x, that is going to tell me the value of y, right?
And Z,
I'm just talking about the plane here. I'm talking about the function of a single variable. So I'll tell you what. Anything of this form is called the function of a single variable.
that I got it. Sphere is a 3D thing.
Yeah, so for that you need a function of two variables.
Yeah, that's-
So that's what I said. Now what you need is z is equals to fxy. Right? So what you have done here is you have done x squared plus y squared plus z squared equals to r squared. This is the equation of the circle in the xy plane. This is the equation of the sphere in the xyz space. That is the 3D space. But what I'm trying to point out is, here yet again you have the same problem. For every xy value, you have two z values. Because imagine a sphere centered, similar to here a circle. For every x value, you have a positive y value and a negative y value. But it is the definition of function which tells me every element of the domain must only be related to one element of the codomain, right? So here I have the same limitation, that every point of xy can only be related to one point of the z, one z coordinate. But in order to describe a sphere, if centered here I have an entire sphere like this, so with every xy I can go upwards and get a z coordinate and go downwards and get a z coordinate. So similar to how in the case of a circle, you take only one branch, either the positive or the negative, in order to satisfy the definition of the function. Similarly, in case of the sphere, you only take either the upper hemisphere or the lower hemisphere. So this is the idea of the function of several variables. From here, in the next class, most probably on Tuesday, we'll hop on to surface integrals and so forth. Thank you.